In this video, we're going to be talking about how to solve for the escape velocity for a rocket, and then also the height that it would reach if it does not reach the escape velocity. So when a rocket is taking off, if you use the conservation of energy, then it has some initial kinetic energy and it has some initial gravitational potential, and then the same thing after. It has some final kinetic energy and then has some final gravitational potential. So it definitely has some kinetic energy to start off with, or else it wouldn't be going anywhere. And it also has some gravitational potential energy. It's on the surface of the Earth. So you would think that's height 0, but we're going from the center of gravity from the Earth. So this at least has a distance that is equal to the radius of the Earth. So this is going to be equivalent to 1/2 m(r), mass of the rocket, v squared, and then minus g MEMR over r. So the gravitational potential formula already has a negative in it, which is gmm over r. And this r is going to be the radius of the Earth because, like we said, it is at ground level. And we have the m of the Earth and then the m of the rocket that are involved. And then afterwards, we actually don't have either of these two. So the reason why both of those are 0 is because for your gravitational potential, if you have an infinitely large r value, then this is eventually going to go to 0 or approach 0. And then for kinetic energy, 0 meters per second is basically the limit at which, if it breaks that 0, it's going to reach escape velocity. If it hits 0, then it's going to come back down eventually because of the force of gravity. So 0 is going to be the limit for this one, and then 0 is also going to be the approaching number for that one. So we have 0 joules on the right side. And then now when we want to solve for the velocity, which is right over here, we can go ahead and cancel out the mass of the rocket, so that's actually insignificant. And then we have 1/2 v squared, and then equals, and I'll add this to both sides, which would send this over to the other side. And then if we finish up the algebra for that one, we're going to multiply both sides by 2. And then square root both sides. Okay, so let's clean that up a little bit, and it'll look like this. Velocity equals the square root of 2 times the constant g times the mass of the Earth divided by the radius of the Earth. The constant g is 6.67 times 10 to the negative 11th. I'll go ahead and write that on the side over here. And then we have the mass of the Earth on the right over here, and then we have the radius of the Earth over here. So if we plug all those things in, we get a velocity of 11,181.4 meters per second. All right, so that's our escape velocity for a rocket or anything else, because as we saw earlier, the mass of the actual rocket did get canceled out. So whether it's a rocket that's 10 kilograms or millions of kilograms, you're still going to have the same escape velocity. Now for the second problem, and we're still going to have the same setup. We're going to have a initial kinetic energy, an initial gravitational potential, a final kinetic, and a final gravitational potential. Now in this case, it's going to be a little bit different. We for sure will have some initial velocity, and let's just say that initial velocity is 9,000 meters per second. So a little bit ago, we said the escape velocity was about 11,181.4. So if we're saying that the velocity now is, we'll say it's 1/2 mass of the rocket times 9,000 squared. We know that 9,000 meters per second, now we know, is less than the escape velocity. So it's not going to escape. It's going to reach a certain height and then come back. So then its initial will still be, we'll put the negative in there, the G E R over RE, again, mass of the Earth, mass of the rocket, and then radius of the Earth when you're sitting on the surface of the Earth. Okay, again, your kinetic energy is going to be 0 because it's going to reach 0 before it falls. But we're interested in finding out how far the rocket goes. So it's going to have some final R value. So what we can do is go ahead and cancel out the mass of the rocket again. We have all of the values except this one. That's the one we're looking for. So after I plug in all my values, this entire side, the sum of the entire side comes out to negative 2.2 times 10 to the 7th. And then on this side, we have negative g times mass of the Earth. So we have negative 3.98 times 10 to the 14th once we multiply those two. And then that's divided by the RF. So if we go ahead and cross multiply these two, then our final RF value comes out to 1.81 times 10 to the 7th meters. Okay, that is the distance from the center of the Earth to the particular height that it's reaching. So if you want to find the actual height from the surface of the Earth, all you do is take this minus the radius of the Earth, which is right over here, the 6.37 times 10 to the 6th, and then you would get 1.17 times 10 to the 7th meters. All right, so to sum things up, when you're doing an escape velocity type problem, you're going to be focusing on your initial kinetic and gravitational potential energy, and then your final gravitational and kinetic energy. And depending on the scenario, if it's the escape velocity where it does escape, then this whole entire side will be 0. If it does not quite escape and reaches a certain height, then you would leave the negative GMM over R on this side, and then solve for that RF. That RF, remember though, is a distance that's from the center of the Earth to the height that it reaches. So if you want the actual height from the surface of the Earth, you would just do a little subtraction at the end and minus the radius of the Earth, and then you would get something like this. So I hope that was helpful to you. Thank you for watching and listening.